Okay, let's go ahead and get started. So the first thing that I want to talk about is homework 3, okay? And basically I said using the Newton's do-while program that was covered in class, write a program to implement the secant method for the following function. And we said the secant method uses 2 points, okay? So let me bring this up. Just doesn't seem like this is quite zoomed in to where. Okay, so some of you guys had some questions, and I know the secant method looks confusing, but it turns out the secant method is actually easier than Newton's method. So just look at this point right here. Okay, this equation right here, this is the secant method. Okay. So what you'll see is this is just Newton's method, right? So if we look at Newton's method, the two are identical. Essentially, they're identical. Okay. So this is just x1 for the first iteration, xn basically they mean the same thing. X naught, it's just the first iteration, xn minus 1, it's just your first guess. The notation's just a little different. Um, f of x naught is this, and then f of prime is this. That's it. Because all this is just slope, 1 over slope. Okay? Because think about it. Slope is the difference of the y's over the difference of the x's. These are your x's. These are your y's. Because y is just f of x. So you multiply times the inverse of slope. So slope is difference of y's over x's, but we just inverted them. And so does that make sense? You got it?
I think so.
Yeah. I mean, if we just had y1 over y naught over x1 minus x naught, that is slope, right? That's slope. Well, that is this. It's just we have taken our y's and put on the bottom, and our x's is put on the top. But down here in Newton's method, you divide by slope. So if I say have 2 over 3, and I take something and divide by 2 over 3, I'm essentially multiplying times 3 over 2. So they just wrote it in this notation just to kind of confuse you. Okay? But that's I mean literally the secant method is Newton's method. It's just you're using 2 points to calculate slope. That's it. Whereas Newton's method, you actually have to calculate the slope either algebraically or do it numerically. That's why the secant method is easier than Newton's method. So I'm going to go over the code. Now I kind of cheated because I said use the do while loop, and I actually wrote the program in the for next and then forgot to change it, but it doesn't matter. Let's just go over and you'll see. This is just declaring variables, right? This is just inputting um, 2 guesses, x naught and x1. This is our step, which we don't even need. I just accidentally left it in there from Newton's method, but we can actually delete it out because it's not important. This is my for next loop, but I really should write a do while loop, okay? But I'm going to go ahead and do the for next, and then you can just see kind of how it plays out. This is just record keeping. So all I'm doing is just exporting my first guess. I'm actually plugging in my this is just record keeping, okay? This is just something that allows me to kind of see where the number is. This is really where I start exporting it down a list because I'm having my I change. So this is just the number, like the first iteration, second iteration, third. This is my first guess, my second guess. This is the function that's evaluated at the first guess. This is the function evaluated at the second guess. Right? Very simple. This is just my y values. So basically, just this and this value, I'm just storing into y1 and y0. Okay? I mean, why not do that? It's simple. Okay? This is just calculating my slope, which is just the difference of the x's divided by the difference of the y's. Right? This is just exporting the slope on my spreadsheet somewhere so I can see it. This is the formula for the secant method, which is Newton's method. My first guess, okay, minus the evaluation of that guess, okay, divided by the slope. All right? That's it. And that's all there is to it. And then this just says, all right, now let my first guess be equal to my second guess, and let my second guess be equal to the, oh, I'm sorry. My very first guess was x naught. Now I'm saying let x naught equal x1 and let x1 equal my new value exported by essentially Newton's method. And then I just loop, and that's it. And then this is where I define my function. Okay? So what I'm going to do is Control A, Control C, and I'm going to paste that into the working document so you can have access to that. All right. Am I clear? I mean, just think of it like this. All of this is record keeping, essentially. So this doesn't have any real meaning other than just inputting and keeping track. This is just calculating my y values. This is just literally calculating slope. This is just writing it down somewhere. This is the formula for the secant method. So if you look here, I mean, that is the formula. You just take f, your initial guess, minus the function evaluated at that guess, divided by slope. This is slope, the inverse of slope. That's all there is to it. Okay? So now let's just run it. So what did I say? I said 1.2 and 2.3, right? So if I run it, we'll go ahead and delete these out. Delete these out. So 1.2, 2.3. What happened? Y1. Oh. Why did that not work? F of x1. By val x. Well, that's really strange because it was working. Let's see. Let's go in and let me run to cursor. So 1.2, 2.3. Let's see. All right. Okay. To step in, so my x value is 2.3. Okay. What's next? Slope equals. Okay.
That's exactly what mine's doing.
All right, 2.9. Okay, looks like it's run. Okay, let me see. All right, I got the right answer. Um, did you use a do while or for next?
Do well.
Do while. Okay, so in my particular case, it's going too far, and I don't know why I'm just getting this error now. Let me try, like, say, for I equal 1 to 3 and see what happens. What was it, 1.2 and 2.3, is that right? 1.2, 2.3. Okay, I know the problem. The problem is we're running out of digits. So essentially we're getting divide by 0 because the numbers are getting too close. So if I just do 1.2, 2.3, I don't have any problem. I have no idea why I just did that. I'm getting some really funky behavior with this. Let me just turn this thing off. I mean, that's really strange. It has to do with precision. I can see what it's doing. But what I'm really confused is why I didn't get this error. I mean, here is the problem, all right, is if you look at x1 and x naught, see how they're the same? So what has happened is where I have 10 um, iterations, they are so close that when the computer divides them out, I'm getting 0. And so I'm getting 0 here on the bottom. Now, what's really interesting is I didn't get this on my desktop. So I don't know if there's a difference in, like, if I have a different processor, if it's the precision. It's hard to say because this is happening on the internals of the computer. But for whatever reason, 10 iterations on the computer I'm using here in the classroom, it's getting to 0 quicker than on my desktop, and I don't know why. That has something to do with internals because all processors, they have just a little bit different architecture and that sort of thing. So maybe on my desktop computer, where it's an older computer, for whatever reason, it doesn't converge to like 20 or 40 or whatever decimal places Excel goes to, and it's showing a little bit of difference. Where on this computer, it's converging almost too quickly. Does that make sense? Do you understand why I'm getting the error? Because there's not a big enough difference. So when I change this to, like, say 5, I'm not having that problem. Okay, 1.2, 2.3. See, I'm not having that problem. So if I come in here and do a do while loop, okay, um, so what do I do with this? I say I have to do a difference, right?
Just set your step equal to epsilon.
Right. Let me, and I should have done this beforehand. I'm sorry. What happened is the other day I went ahead and wrote this code, and then I told you guys, oh, go make sure you use a do while loop, and I didn't use the do while loop. So, but you guys get what's going on, right? I will fix that because it's not worth. I think it's going to waste too much time for me to figure out how to do it, even though it may only be a minute or two. I just don't want to do that right now. Okay. All right. So the secant method is pretty simple, right? All right. So what I want to do now is I want to show you guys something that I think is kind of cool. Okay, so the power of, power of numerical analysis is you can apply this to any continuous function. All right. So I went in and I created a function. Okay. Oh man, come on. Copy. There's a problem. Um, there we go. It had to do with resolution. I knew the resolution was wrong. I could just look at it and tell. All right, so here's what I want you to understand is sometimes your functions aren't necessarily like these nice, neat algebraic functions. Sometimes your functions can be a response to, say, a computer simulation in of itself. Okay, so imagine that you have some type of simulation that you've done in SolidWorks, or you're doing some type of aerodynamic or fluid simulation. So your output is actually a computer going in running this finite element model that, I don't know, let's suppose it takes an hour for the computer to run that. And so your output may just be one data point, all right? I know several years ago when I was working on a project when I was at Old Dominion for Homeland Security, we built kind of a model, this really large-scale model in conjunction with this research group up in D.C. We had hundreds of variables in this model, and as I recall, I think it took about 8 seconds per run to run the model. Okay? Like, well, 8 seconds, okay. It's like, yeah, but we had like 100 independent variables. So when you start thinking about creating the response space for that, it doesn't take you long to see how that multiplies out really, really quickly. So let's just say that each response variable just varies from 1 to 10, all right? And you want to go through all the possible combinations at intervals of 1. Well, that's 10 to the 100th power. That's a huge number. That's a 10 with 100 zeros. You're not running that on any computer, okay? So if you want to find out where this model is peaking at, okay, or where it's peaking either high or low, whatever it is, you have to come up with some more sophisticated way of culling it down. You can't just draw a graph. And so, for instance, I don't know, did you guys notice while I'm sitting here and was talking how long it took this to run? Did you pay attention to that? Well, let's just do it again. All right, so we're talking. Second hand's not working, but I'm just going to keep on talking. Watch it compute and that sort of thing. So this is running on a cloud somewhere, and it's going to give me an answer here in just a moment. Okay, how long did that take? 10, 15 seconds, something like that. But the function that I'm plugging in here, I'm going to explain a little bit about what this is. But imagine this is like a computer simulation running, okay? So we're just kind of taking for granted this graph here that just ranges from -2 to +2, all right? So let's suppose that I had another graph that comes up here that's just y equal x, and I want to see where these two, say, intersect somewhere around, I don't know where it would be, maybe somewhere around here. Where would that be? Well, it's like, well, just graph it and see where it crosses zeros. You don't understand. When you're dealing with multidimensional problems, you don't just graph something. If I do intervals of zero point 0.1, I had to go through 40 of these iterations, right? You see that? You have 2 on the negative, 2 on the positive, break it up into 20 apiece, 40. Now, what happens if I had a third dimension? Well, multiply that by another 20. I'm up to 8,000. All right. Well, that's going to take 20 times longer. So if this took 10 seconds, multiply that times 20. That's 200 seconds. We're already waiting 3 minutes. Go 4 dimensions. 3 minutes times another 20. Wow, that's an hour. Ooh, I don't know if I want to sit here an hour. We'll go 10 dimensions. Oh, that's going to be like 4 years. Okay, so you either come up with some more sophisticated ways of trying to get your answer, um, or you try to run it on a cluster of computers or supercomputer or whatever it may be. Well, it just depends on the problem. But let's suppose, for instance, that I want to know where this peak is. Well, for a problem like this, I may be able to go in and analytically determine, okay, it's at 0, all right? But if I'm doing some type of simulation, so for instance, let's suppose that I'm simulating the horsepower and torque of some engine. I work for Toyota or something, and I want to see how that horsepower and torque is a function of how much fuel I put in on each pulse, or maybe the timing. I have these solenoids instead of having like um, a camshaft that controls my valves, and I'm actually doing. And I just want to see how all of this actually relates. Well, you can build the engine and test it, which is how you used to do things, and how you still do things to actually see how it's going to perform. But if you can simulate this in a computer, now you can start changing all of these parameters to see how it's theoretically going to respond, okay? And you can start optimizing within the computer itself. And this is kind of how a lot of modern engineering is actually done. But even then, you're not out of the woods, because you can have many, many variables, okay? And you want to figure out where that peak is. What do you do? Well, it just depends, but I'm going to show you an approach. Okay, so this function right here is a function that I came up with. Okay, and you may say, well, why did you come up with a function that looks like this? Like, what purpose are you trying to? What's your purpose here? Okay, well, what I did is I created a function that I called prime pi. Okay, so let's suppose I take numbers, I don't know, let's just go 1 through 20. And I type in prime pi of whatever this number is. What it's going to do is it's going to give me the nth prime number. Okay? So the first prime number is 2, the second prime number is 3, the third is 5, the fourth is 7, the fifth is 11, the sixth is 13, and that sort of thing. So do you understand what that function does? Okay, so let's take a look at this function just for a moment. Here is the function. Okay, right here it is. Okay. Now, I'm not asking you to understand this function, because what this function does is it goes through and it determines whether or not a number is prime or not, and then it adds 2 to it and determines if that's prime or not. If it is, it counts it. If it's not, it adds another 2 to it. Why do I add 2? Because I'll have to do, I know all prime numbers are odd, except 2. And that's why I put this first one in. If p equals 1, then equals 2, n equals 2, go to 10. So if it's 2, I say, all right, that's the only even prime number. I'll skip it. If it's odd, all I have to do is then test 3, 5, 7, 9, 11, 13, that sort of thing. Okay? That makes sense? You don't have to understand the details to this. All this is doing is giving us the nth prime number. But it took me a little bit of time to do this, and I wrote this program like 10 years ago and lost it, and couldn't get over the fact that I lost it, and finally just had to buckle down and rewrite it. Okay? So what I'm doing is I'm creating a function where I take this quantity right here, x squared plus the square root of 2, and I am raising it to p to the n, which is prime pi, and then I'm taking the log of that, squaring it, and taking the negative of it. Okay? So I do this for all the numbers, say from -2 to +2. All right? So what I want you to get out of this is function is not trivial to calculate. If I give you a function like x squared plus 2x, 3x plus 1, and I say x is equal to 0.1, how do I solve that? I go 0.1 squared plus 3 times 0.1 plus 1, right? That's easy. If I tell you here that x is equal to 0.1, how do I solve that? I take 0.1 squared, add the square root of 2 to it, and another thing I did is I am summing this from 1, I equals 1, or I'm sorry, n equals 1 to infinity. Now you say, yeah, but you only had 500 here. Yeah, but the reason why I put 500 here is because mathematics can't handle infinity. All right, so here is the function that I created. So how do you solve that? Well, you say, okay, let's let this quantity, I'm going to figure out what the first prime number is. That's 2. I'm going to take the log of 2, I'm going to take the square, I'm going to square it, I'm going to take the negative of that, and then I'm going to raise this quantity to that power, hold on to it, then I'm going to search for the next prime number. That's 3. We'll take the log of 3, square it, take the negative of it, and raise this quantity to that power. Search for the next prime, that's 5. The next and that. So you see how that's a little bit of work? That makes sense? All right. Now, this is a function that I call we, W-I. Okay? And this is something I came up with. All right? So it can be anything. So if I come in here now and I take a number like 0.1 and I say we of point, let's make it, let's do this. Let's make this like 2. And I say we of 2. You see I calculated that? Let's suppose I make it 1. All right. Let's suppose I make it 0.4, 0.3. What do you notice about it? But what else do you notice?
Takes a little bit longer.
Right? See that? Okay. So it's taking a little bit longer. All right. Now I could have some function that represents a simulation that when I hit enter, it may take 10 minutes or 2 hours or whatever it is. Now, if I come in here and I do something like this, 0, then 0.1, 0.2, and I run this down, say, to like 1, and then I double click this. Did you see what happened? That took a little bit, right? So now let's suppose I take this function, which I graphed in Mathematica, and I want to set it equal to where it is equal to itself. How do I go about doing that? Okay. Well, here's what I can do. I can come in and I can use Newton's method to solve that. Okay? So I'm going to come in here and I'm going to create a function. Uh, you know what I did? I have it graphed over here, and it's having to update my graph. So I didn't think of that when I did all this kind of offline. Uh, there we go. All right. All right. Well, maybe not. I don't know if it's working. All right. Anyway, while that's working, do you understand now how the complexity of this? So what I did, okay, yeah, okay, yeah, guess it's kind of pausing between. So it says calculating for processors, it's at 5%. Yeah, mental note, don't do this again. Okay? That could be a problem. Anyway, I'm giving a really good demonstration of why you need a more sophisticated technique than just brute force. Is that clear now?
Mhm.
Because what I did is I went from -5 to +5 in point 0.1 increments, and I calculated we, okay, all right. I calculated we, there we go, which is this blue line, and then I just have y equals x, which is this red line, and I want to see where they equal to one another, all right? So calculating this blue line, this is what took the bulk of my time. Does everybody see that? Do you see why it takes a long time?
Yeah.
Okay, you got that. So this function isn't just some simple function.
Mhm.
Okay, so I want to see where y equals x right here. So what I'm going to do is, while my computer isn't locked up, I'm just going to go ahead and delete these, okay? Because sometimes, like when you refresh, it wants to go in and recalculate the cells, and I don't want that to happen, all right? So what I want to do now is I want to come in and determine where that complicated function that involves x is just equal to x. Okay? So the function is just this. It's f1 of x is equal to x minus w of x. And I define w of x right here. So the way I actually calculate this big summation is just this function. I call this prime pi, okay? So prime pi is a function that I created, okay? It's this iterative function. We is a function that is an iterative function that's basically like, you remember watching the lecture where I calculate pi and I calculate sine and I use Taylor series expansion? That's all that's going on right here. It's just summing it up. It's saying, all right, do while diff is greater than epsilon. I say I want epsilon to be 6 zeros and a 1, and then I just start adding it to itself until when I add another term, it doesn't increase by epsilon, all right? So I'm calling a function that's calling a function. You get that?
Mhm.
So this function doesn't exist in Excel. These are functions that I made, all right? And I am referencing that using a Newton's method. So all I'm doing here is clearing the contents. This is just a regular run-of-the-mill Newton's method. You already have covered this. But f of x now is a complicated function, right? And I want to see where that function equals essentially 0. So I'm going to run it into Newton's method, and I'm going to guess. I'm going to say, I don't know, let's suppose the answer is 3. Boom. Well, it converges to 1.07. Let's suppose that I say, well, let's try, I don't know, let's suppose it's 0. Uh, it's got to calculate that first 0, and it turns out the closer you get to 0, the more it actually takes to calculate that first iteration. So it's spending all of its time right now evaluating the function. It's probably not even gotten into Newton. Oh, there we go. There's our first iteration. Oh, now it runs over to 2.65. Well, how long is that going to take? May not take as long as 0. Let's give it a minute. See. Maybe I should have picked 0.01. I actually I may have, and the reason why, now that I'm thinking about it, is if you think about evaluating at 0, the slope is 0 there, right? Because it's at the top,
Mm.
so it shoots out to infinity. Right? Shouldn't have done that. That was a bad guess. And I'm kind of seeing that by this guy right here. So let me see. Is there any way that I can... Yep, I screwed that one up. Oh, no, no. Bad guess. 0.001. Let's try that. Yeah, maybe that'll work. Do you see why 0 was a bad guess? Because the derivative at 0, it's a horizontal line and it never crosses the x-axis. So your next guess is infinity. So you have to, and so it's like, well, how do you fix that? Well, that's where you need error checking, which I haven't written that in. So what happens is sometimes if you find that when your evaluation at the function of 0 has a slope of 0, you say, well, let me move just a little bit, and then, oh, okay, it's not 0, and then I'll take off from there. And your more sophisticated programs actually have those types of checking mechanisms in them. Shouldn't have picked 0.0. I should have. I picked 3 and it worked, right?
Yeah.
Okay. Here's what I'm trying to get you to see is this actually seems to work faster on my desktop computer, but it should grind through here in just a minute. I should have picked like 0.1. But instead of having to evaluate maybe hundreds or thousands of points, there we go. So in what, 6 iterations, it actually figured out where the answer is. I don't know why it's still doing that at this point. It should not, but I don't know, maybe it got something happened. So do you see the value of a method like Newton's method? I mean, you can, so instead of me having to actually graph that, which you saw it was taking forever and I was worried that it was even going to show up, I'm able to go in and determine the optimal answer, which is 1.76388, in just 6 iterations. So I'm only having to do 6 evaluations of this complicated function to determine what that optimal answer or what that root would actually be. So what I'm trying to show you is that Newton's method can be evaluated on any continuous function. Okay, now a lot of times you need it to be well behaved, and if it's not well behaved, we're going to talk about what to do to make it well behaved, which is using some type of approximation function. All right? All right, so I don't know. I'll just kind of, oh, wait a minute. There we go. I don't know what it was really doing. All right, so I think that's kind of cool. I mean, that the function that I'm calling can be anything. I mean, this could be calling, like I said, some simulation that maybe takes hours to run. But just with a few points, you can kind of start to see the behavior of this function and kind of home in on what that root or what that optimal value would be. Okay? Does that make sense? Any questions? All right. All right, now what I'm going to do is I'm going to talk about Newton's method in multiple dimensions. Because the great thing about Newton's method is it's not just for one dimension. And last week I talked about that. Yeah, here was the formula. Remember last week when I talked about this? How we used the Jacobian? All right, so here it is in multiple dimensions. So the function that I have is I have these two functions right here. This function, and I just have a linear function. Okay, so basically I have x times the log of xy plus 1 minus x squared plus x times the log of x. So basically I have these two simultaneous equations. So let me see. Let me do this. So let's kind of write this out so we can actually see what this is. This is x times the natural log of x, y plus 1 is equal to x squared plus x times the natural log of x, and 2x plus 3y is equal to 6. Okay? So I want to know the values of x, y where these simultaneous equations are equal to one another. So have you ever seen anything like this? Never have. You've probably, the things you've worked with are something like 3x plus 2y is equal 18, 4x minus 9y is equal to like negative 24, right? That's probably the extent of simultaneous equations you've worked with. What do you do when you have nonlinear simultaneous equations? Okay, here's one possibility. So we're going to start off easy. One possibility is you write one equation in terms of another equation. So you say something like x is equal to 6 minus 3y over 2, right? And then anywhere you see an x, you plug in 6 minus 3y, right? So do you see how now your whole equation would be written in terms of y? Does that make sense? And then you just solve for y, plug that in, and then go in and solve for x, right? Now, this only gets you one level, though, because what's going to happen is, even though you've essentially eliminated one equation and you've written it just in terms of one variable, you're still not going to be able to get it in terms of just like y equals something. So you're going to be left with what we discussed earlier, a problem like x to the x is equal to 20. But how do we solve x to the x is equal to 20? We put it in Newton's method, right? But we're going to get something like, y times the natural log of y times y to the y is equal to 18 or something. I mean, I'm not saying that's what we'll get, but you're still kicking the can. The only way to really solve this is still by using something like using Newton's method, okay? Now, here's the question, though. What happens if I have two equations? What happened to that other equation? Did it just disappear? Okay, I don't know what happened to it, but obviously it disappeared. Yeah. So what happens if I can't write one equation in terms of just one variable? What do you think we do? We use Newton's method for multiple variables. So how do we do that? I bet you think it's hard, don't you? It's not hard. That's why we did the work and we calculated the Jacobian matrix. All you have to do is create a guess, okay, of x and y, and you just plug into this formula. That's all you do. You just take that guess, okay, and you subtract the inverse Jacobian matrix times the function evaluated at f x and y, or xn. All right, and this is real easy to do. So we've already covered how to calculate the Jacobian matrix, right? We know how to do that. Now we're just going to calculate the inverse of the Jacobian matrix. that is really easy to do. We're going to use Excel to do that. So the way you calculate the inverse of a matrix is you just type in this, okay? And then you, oh, let's see, how do you do this? Well, one, you can just type in this formula, which is what I have.
Don't you highlight all the cells that you need?
That's
Hit
it.
Control Shift Enter?
Control Shift Enter, is that right?
I think so.
Yeah, I forget how to do it. I mean, it's real simple. You search it on the internet. I had to sort look it up. But all I'm doing here is I'm calculating. So if I plug in a value like right here, you see how that inverse changes. So this is just the Jacobian matrix. This is the inverse of the Jacobian matrix. Um, and it's really simple to do, and we'll do it. I mean, look, it's easy to do. Inverse of a matrix, Excel. Yeah, so you find, you highlight, you type in this, and then you hit a press Control key, Shift key simultaneously, Enter. So, so we find the matrix by highlighting the cells we want to place. Right, matrix B. Look, I don't remember how to do it. I did it the other day. I've got some problem with the computer. I don't know what's wrong with it. Oh, there we go. Okay, let's just forget that a moment. Um, look it up in YouTube. It's easy to do. All right. Now what we're going to do is we're just going to plug in where it's actually evaluated at. Okay, what our guess is, and then this is, well, this is where let me plug in like 1 and 1. Okay. This is what the actual evaluation of the functions are, okay? So whatever functions I'm using, this is my x, this is my y, and I just plug in those equations. So this one's easy to see, 2x plus 3y minus 6, all right? So it's just 2 times g20 plus 3 times g21 minus 6 gives me this. This is evaluating that big log function. And this is just multiplying this matrix, the Jacobian inverse, times where the value that it's being evaluated at. Okay? And that's this number right here. Okay? And then this is where I subtract G20 minus I20, which is my initial guess. Okay? And then these become, on the next iteration, my new guess. Okay. So let me run it, and then I think it'll, so input the value of x. So let's guess, I don't know, 0.1. The value of y, 0.2. So what it did is it wrote these values, all right? So my first guess was 0.1, 0.2, all right? Does that make sense? All right? So then I go in and what have I got here? Oh, yeah, okay. The problem is that I see my Jacobian, it changes. So let me do this real quick so we can kind of step through this. Let me do this. MSGVOX. All right, there we go. This will help out. So 0.1, 0.2. All right. So do you see how these values are in right here, 0.1 and 0.2? Okay. Now, do you see how those values now were transferred over? See, what happens is my matrix changes. That's why when I looked at it a second ago, it's like, oh, those aren't the right numbers. So now what I do is I bring over 1.426 and 1.049, put them in here. Now watch this. And I have to recalculate the Jacobian matrix each time because that's dynamic. And do you see how these numbers start converging on a number? And I basically just report them here. And so once I get to like 6, 7 decimal place, is it stops. All right, I don't think I did a very good job explaining that. Tell me what you didn't get about it. Or did I do a good job explaining it?
I think I understand
Okay.
the concept.
Okay.
The code, I'm not sure.
Okay, so the code is real simple. All right. I'm doing the work in the spreadsheet in this particular case, kind of for a learning exercise. Anything you can do in the spreadsheet, you can do in code. All right. So the Jacobian matrix, I'm taking care of with code. We already know how to do that. The inverse Jacobian matrix, I'm taking care of using an Excel formula. Okay? The guess is just the guess. I'm just throwing the number in. Here, I'm taking care of the evaluation of the guess using Excel formula instead of using it in my code. All right? Here is I am multiplying the inverse times the value at which the function is evaluated. Okay? So think of it kind of like my z value.
Right.
Does that make sense?
Yeah.
Here I am just subtracting, and let me put in another number here because I don't want these to be zeroed yet. Here is the inverse matrix. Here is where it's being evaluated. Okay? Here is where I multiply the two together, and here is where I take the difference. And then I take these numbers, put them in here, recalculate the Jacobian matrix, and do it all again.
So the Jacobian inverse matrix is linked to the Jacobian itself.
It is.
Okay.
Yes.
Why does it constantly change if the Jacobian is 5? Does the Jacobian change due
Yes.
to the guess?
Yes.
Okay.
Yeah. So if you think about the Jacobian matrix, depending on what your values are, that number, because the Jacobian matrix can be a matrix with formulas in it. That's how you're taught in like calculus or differential equations. But when you actually put numbers, it's just like the derivative. The derivative is a formula until you say at what point, and then you just plug that value in and it becomes a number. So that's why the Jacobian matrix changes each time, because your guesses change. Okay?
Yep.
Because the Jacobian matrix, it's just the slope in two directions at each individual point. Does that make sense?
Yes.
So now, if I come here and I show you this, I want to show you how this relates. So when I come down here, and I guess, all right, help me find this guy's.
You control it.
Yeah, but I just had it. That drives me crazy, you know.
What are you looking
I'm looking for the Jacobian, the formula for multiple variables. Oh, there it is. I know it wasn't crazy. This formula right here, okay? I want you to see how it relates, okay? So the Jacobian inverse is this guy right here, all right? The function where it's evaluated, the actual z value, is this guy right here, all right? with these numbers being plugged into here. Okay? The whole thing multiplied out these cells. The whole thing that is evaluated are these cells. Does that make sense? Then these numbers get moved into here, and it's started over again. The Jacobian matrix changes, with which changes the inverse, which when multiplied out changes, which when you plug into the formula changes, when multiplied out changes, and that's how the iterative cycle works in 2 dimensions. So it's really simple, I guess is what I'm trying to say. And I feel like that I'm saying what needs to be said, but I don't know that I'm saying it in a way that satisfies just how simple it actually is. Because I want you guys to say, oh yeah, that's easy. When you say it's easy is when I feel like I did my job. So what's not easy about it yet? We know how to do the Jacobian. This has been covered. We've already did a homework on it. I've covered it in class. You got that. The inverse is done Excel. It does it. It escapes me just a second of how to do it, but it's super simple to do. Watch a YouTube video in 20 seconds. You're like, oh, that's simple. Okay? The guess, I just pick numbers. The evaluation of the function here, it's just plugging into what the function is with 2 variables. Okay? Multiplying these 2 together is easy also because Excel does it for you. It's just matrix multiplication, M mult. So you multiply this matrix times this matrix. This right here is just subtracting out this value from your initial guesses. And then these just get copy and pasted and put in there. So if I actually do this step by step, I'll pull it down here to where I can see it. Plug in a guess, 0.1, 0.2, boom. And all that is just writing it out till it converges. Does that make sense?
You do the first 2 cells in the f of x of y in the code, and just tell it to put the values in those 2 cells.
You could. You could do all of that work in the code. The bulk of what I am doing in the code is just calculating the Jacobian matrix all the way to here. And then all I'm doing in the code here is just moving stuff around and then just taking the difference between the 2 guesses. So the code in this particular example is not the one doing the work. The work is being done inside of the Excel spreadsheet. But I could go in and instead of using the code inside of the Excel spreadsheet, you could actually write that code in VBA. I just chose not to do that because I wanted to get it working, and I wanted you to see what was actually going on, kind of so I could compare it, sales to the formula itself. Whereas if I did it all in the code, I felt that it would be a little bit confusing.
I agree.
You get that?
Yeah.
Okay. So what I want to do now is I'm going to do a little bit harder example. And I realize we have about 10 minutes left. Okay. So in this example, here are the 2 functions that I have. And you've already seen these. I had you guys do a Hessian matrix on one of them. So this is what I have. X times the natural log of xy plus 1 is equal to x squared plus x times the natural log of x. Then I have 2 raised to the xy times yx is equal to 5. All right, so how would you solve this?
Be a toughie.
It'd be a toughie because you can't write x in terms of y in either equation. You're stuck. I mean, think about it. Before, I could at least kind of give you an approach to say, well, we could write one in terms of the other and then substitute it in, and then we could use the Newton's method for one variable. In this case, you can't do that. You are truly solving two simultaneous nonlinear equations simultaneously. How about if you had 3 or 4 or 5? You have no alternative. You have to use something like Newton's method. And that's what we're going to do. So I'm going to come in and I'm going to say, okay, for some reason this computer is just not, it's just, so what I did in this particular case is I actually, instead of, I think I used I actually used a for and x loop, okay, instead of the do while. But I should use a do while, but I didn't. But let's just change this to like 20 so it doesn't blow up. All right, so now what I'm going to do is I'm going to guess. All right, I don't know. Let's guess 0.1, 0.4. Okay, so my first guess, 0.1, 0.4, plug it through one iteration, 2.83, 0.7. The next iteration. So let me plug in, what was it, 0.1, 0.4. Let me go ahead and bump this up. Let's just go ahead and make it 50. 0.1, 0.4. So you see how it does converge? Now when you get into multiple dimensions, sometimes it takes longer to converge. Now this is what the convergence actually looks like. So my first guess was 0.1, 0.4. It shot over here to 2.83.7, shot back to 1.72.5, shot up now to 1.46, and then it come over. But you can actually graphically see how this thing is kind of homing in on the right answer, and it's converging, which is kind of cool, I think. And then if you had 3 variables, you could actually draw this like in 3-dimensional space and kind of like watch it walk around. And this graph will be dependent upon my guesses. So if I plug in like a 1 and a 2, see?
Want the closed Engr to be?
Yeah, and I mean it's very difficult to know. This is completely dependent upon the functions you have and where you guess. I mean, I plug in another guess of 1 and 0.1. Well, in that particular case, I had a problem. I had like an overflow, and we're going to talk about this in the class. I mean, it look sometimes it's just not. It doesn't work. Okay. Sometimes it doesn't converge. Sometimes it does weird things. So I'm going to show you an example where it does something weird. Okay. Chaos. I love chaos. It's what drives the world. It's the meaning of life. All right. So let me plug in. Let's plug in a guess. 1 and 1. Yeah, I did something wrong. I deleted something I shouldn't have. That's why I don't save it. I realized what I did. I deleted So let's plug in a guess of like 1 and 1. And look what happens. These are my X and my Y values. So let's just kind of go through and look. My first guess was 1 and 1. I had it skip that and just report the next one. Then it goes here and here and here. And then it comes back to almost where it started, if you look at this. That's point like 18. Not 18. I don't know what point that is. That's 18 and 5.6. Trying to see, where's this one? Point 0.5, is that right? Oh, yeah. Right here it is. So this is 3.5, 5.8, then I go down here, this is 3.5, about 5.8. So this is a chaotic function. This is true chaos. There is a pattern, but it doesn't repeat exactly each time. Okay? So in this case, this did not converge. So you have a limited number of possibilities. Okay? Here are your possibilities. It can either converge and give you an answer. It can diverge and go to infinity. It can cycle on a regular pattern, which basically means that every so often the iteration that it kicks out is the same as your first guess.
So it's cyclic.
It's cyclic, exactly. Which that's easy to see. Like if I guess 1 and 1, and then like 18 iterations later, it gives me 1 and 1. It's like I'm done because I mean it's just gonna cycle, or it can cycle in a chaotic pattern like this. And so the answer then it becomes, well, how do you know? The answer is, well, you don't know. That's where it actually, where you have to get into more sophisticated techniques that have like they kind of have damping factors to kind of slow it down if it detects something one way or the other. Okay, and we're going to talk about this in the class a little more. Okay, I mean some of these techniques get really complicated, and we won't be covering those. Those would be like graduate level numerical analysis, or like a numerical analysis 2 graduate level courses where you would talk about something like that. We're just going to talk about the fundamentals, which is really, I think, once you kind of understand the fundamentals, then you could say, oh yeah, I see why you would have to do this or that, something a little more complicated. Okay? All right. Did you guys learn anything today? It's pretty neat, isn't it? I mean, and this is what you have to do when you get into really kind of hard problems. You have to start using numerical analysis techniques because this is where calculus and differential equations break down. It's hopelessly complex, too complex, and so you have to start saying, well, what do I want out of this? And as an engineer, what you want out of it is an answer. You're looking for this, okay? You're not necessarily looking for some symbolic equation, all right? Okay, so where we're going to go from here then is I'm going to start now kind of jumping to letting the computer do some of this work for us, because Excel, as you guys probably know, has some of these functions built in through goal-seek and solver. But now you guys kind of have some insight as to how these algorithms actually work inside of Excel itself. And we're going to start doing some interesting things. Okay? So now, here's what I want you to think about. One last thing is I'm going to go in and type in Newton's method for optimization. Okay? And when we go down here and look at the formula here, you see this formula right here? Okay? Very similar. So this formula is very similar to this formula. which is similar to this formula. So intuitively, I'm going to explain this formula to you. This is Newton's method. This is simple. This is simple. We're using the Hessian matrix instead of the Jacobian matrix. Do you know why we're doing that? It's real simple. I'll tell you why. Because we're taking the derivative of the derivative. So guess what the derivative of the derivative is? The second derivative. So it turns out that Newton's method for optimization is just Newton's method for the first derivative equation. And that's why you end up using the second derivative. And this gradient is essentially the first derivative of you plug in your initial guess, and your gradient is your first derivative information, and I'll talk about that next week. So it's the exact same thing. You could go in and not even know this formula or understand it, and I could give you the problem, and I guarantee you could figure it out. Because all you have to do is just take the curve or the surface of whatever that first derivative curve or surface is, then all you do is just set that equal to 0. That's it. And you don't even have to understand this algebraically. So when you think about this, if you have a function, say it's a cubic function, and it looks something like this, all right? So what does the first derivative of this look like? It's parabolic, right? And it's parabolic, it looks like this. Agreed? Because it's wherever these line up with where the second derivative or the first derivative is equal to 0. Correct? And then what does the first derivative of this guy look like? It's linear, like something like this, right? You agree with that? So all you're doing is just using Newton's method to figure out whether the first derivative curve is equal to 0. But in the process of doing that, you're using second derivative information. That's why you have to use the Hessian matrix instead of the Jacobian matrix. Right? Just taking the first derivative of the first derivative. That turns out to be the second derivative. We're using matrices instead of just a number, one element. So that's the intuition to why you use the Hessian matrix. All right? And you can actually, if you look at this, Newton's method for optimization is they went ahead and went to multidimensional, but all you have to do, they're using like Taylor series, but this is really what I've got it, I think in my text I wrote it down, but all it is just your guess minus the evaluation of your first derivative divided by your second derivative. But your original formula is just the function divided by the first derivative. But you're just moving up a derivative. All right. All right. Did I say anything today that doesn't make sense? You see where we're going with it? See how it can be useful?
Especially whenever you look at the two ratio wacky powers and signify.
Yep.
That'd be really hard to symbolic if you just put numbers in there.
Well, I'm going to, here's what I want you to think about, and next week we'll talk about this. Forget this guy even exists just a minute. I want to ask you a question. How would you graph this guy? And it's tough, isn't it? See, even graphing a function like that is not trivial. All right? So I'm going to teach you guys how to graph something like that. And it turns out to graph something like that, you actually have to solve the equation each time. So even to graph this, you have to use Newton's method. It's actually not that hard to do. What you do is you just create a table of x and y. You say, all right, 0, 0.1, 0.2, dot, dot, dot. And you say, all right, at point 1, I plug in point 1 here, point 1 here, point 1 here, point 1 here, point 1 here. Oh, then I solve for where y is equal to 0, and wherever y is equal to 0 is what I plug in here. That's how you actually graph it. And the geometrical interpretation of that is really, this is a surface, right? So we could move everything over onto one side of the equation and just have something like z is equal to this big function, right? And see that as an elevation, right? Then you let z be some value, like say z is equal to 5, and then you solve for the values of x, y, and what you do is you take a slice of that function. So imagine this bottle of water that I take and run a piece of paper through it. That cross section at whatever height is what this function actually is. So you remember a couple weeks ago when we were talking about, you said you saw a picture of a four-dimensional object. Remember that? And I said, well, that's really easy to do. All you do is just take a cross section of it. You just have to reduce the dimensions. So what you end up doing is taking a function like this and you create a contour map, just like an actual contour map of the mountains. If you think about that, that's just slices at different points. And so that's how you actually graph it. So that's how you graph higher dimensional objects. You just take a cross section of it, and then you change that cross section, and it looks like it's moving or something's coming out of the page because you let that be a time dimension is what you do. All right? All right, that's where we're headed. So buckle up.